Hi, this is the first lesson in circular motion, mainly focused on A-level syllabus like Edexcel or Cambridge or even International Baccalaureate. Okay, so first we'll think about when object moves on a circular orbit, what could be the direction of acceleration of the object? Say for example, when object moves on a straight line, a rectilinear motion, if the object moves on a straight line, and if the object is accelerating at different instances, when the object is here, say when t equals 0, at here t equal t1, at this point when t equal t2, the direction of acceleration should be along the direction of velocity, and the direction of velocity will be along the straight line because it's moving on a straight line, right? So if we think about circular motion, when object moves on a circular path, always the displacement will be, at any instant, the displacement will be along the tangent of the circle. At any instant, the displacement will be along the tangent of the circle. So the velocity also must be along the tangent, because velocity and displacement always parallel to each other. So at any instant the velocity should be along the tangent, but the speed, that is the magnitude of the velocity, could change. For example, when object moves on a vertical circular path, you know that the velocity changes due to change in direction, as well as the speed also will change. If you have a string attached to a bob, if you keep the string initially horizontally attached to a point O, let it move freely, so it will move on a circular path. When it is here, the speed will be different compared to when it is here, because when it moves down, it's losing the gravitational potential energy, so there will be gain in kinetic energy if we ignore the drag force. So the speed is moving on a circular path, but the speed will change. So when object moves on a circular path, it's not necessary to say the speed is constant. It's an unwanted statement. The speed could change when it moves on a circular path. Okay, so here I told, when I explained about the linear motion, when object accelerates on a straight line, always the direction of acceleration and the direction of velocities are parallel along the straight line, because it's moving on a straight line, right? So here we are going to analyze what could be the direction of acceleration at an instant. Right? So here we are going to find the direction of acceleration at an instant. Say for example, when the object is at point A, then later it's at point B, its velocity is changing due to change in direction. Maybe the speed also could change, as I told, in vertical circular motion, whatever it is. So at an instant, say for example, when it is at point A, what could be the direction of acceleration if it is moving on a circular path? Okay, so at an instant means I should consider, that means actually, at an instant the object should have acceleration, but at that instant it can have only one velocity. We define the acceleration as rate of change of velocity. Is it? That's the way we define, or in terms of calculus, dv over dt. So at an instant means t should be much smaller. T should be, during a smaller time, we should consider two different velocities. At an instant, it can have only one velocity, because at a point, object can't have two different velocities. It can have only one velocity. But at that instant, the object has acceleration. So to get the relationship for acceleration at an instant, in terms of calculus, we say dv over dt. That means small change in displaced velocity during small time interval. So we'll consider, it could have, the speed might be changing. So we'll consider very close at 2 points. I consider point A, and I'm going to find the direction of acceleration at point A. So I'll consider another point, much closer point. Can't see when I mark it on the board. So what I'm going to do, I'm going to draw an enlarged diagram. An enlarged diagram, I'm going to draw the same thing like this. So point A, this is point A. At that moment it has velocity v1. So the next point, maybe I can call it as A1 or B, whatever it is. Very close a point, but I am going to draw it as an enlarged diagram somewhere here. That is B. So at that point B, it will have velocity along the tangent. So A and B are very close up points, and the time taken for the object to move from A to B is very small. If I say the time taken is delta t, that is almost equal to 0. Almost equal to 0. So that means during that time, change in speed is negligible. So I'll take the speed here also the same as this one, V1. Understand? But I am not saying it's moving at constant speed. Careful. Here I want to find out the direction of acceleration at an instant at point A. So I need to consider two much closer points where the velocity is what could be. So A and B are much closer points with a separation delta S. Delta S, very small separation, and the object moved from A to B during a smaller time delta t, which is almost equal to 0. You can imagine the smallest amount of time, any amount of time, but which is not equal to 0, but almost equal to 0, very small time. So these 2 points are much closer points, but I drew it as an enlarged diagram, right? So during the time, the change in angle, central angle, could be delta theta. So A and B are much closer points. This could be delta theta, or delta theta. I mark it as delta theta. Okay, so why I put same speed? Because the time taken to travel from A to B is very small, so it's almost the same 2 points. So the speed has no significant change, but direction has a change, right? Okay, so I need to find the change in, I need to find the direction of acceleration. What could it be? So I know that change in velocity delta V is equal to the final velocity Vf minus Vi. I put F and I, but they have the same speeds. So that is the final velocity Vf is going to be initial velocity plus change in velocity. Okay, now we'll think about the vector diagram for this change in velocity. So A and B are very close points, I already told that. So final velocity is along this time. This is the direction of final velocity. Initial velocity along this direction. When I add the vector delta V, I can mark this with vector signs like this way. Vector sign. So delta V is the change in velocity. I need to find the direction of acceleration, means I need to find the direction of change in velocity. Okay, so we'll see the final velocity is along this direction. So initial velocity Vi, that is this direction, that is Vi, the numerical value V1. So I'll put it as Vi or V1. With that, when I add the change in velocity, I get the final velocity along this direction. So the final velocity along this direction. This is final velocity Vf, that also V1, because I told A and B are much closer point, no significant change in speed because delta t is almost equal to 0. So I want to find the acceleration at an instant. So that's the purpose of it. So Vf also equal to V1. So I can say Vf equal V1. So I can remove this Vi now because I'll put it as V1. This is V1. So the change in velocity, the direction of change in velocity along this way. This is the direction of change in velocity. Vector addition rule. V1 plus delta V gives the V1, that is the final velocity. This is the initial velocity. So we know what is the direction between these two velocities in this diagram. So if I extend this line like this way, tangent, and if I extend this line also, we know this is delta theta. I already told the velocity will be along the tangent. So this is 90 degree. This also 90 degree. Both are 90 degree. So total angle is 360. So this angle will be delta theta. Okay, because 90, 91, 80, this is delta theta. So this will be delta theta, this external angle. So that means the angle between these two tangents is equal to delta theta. That means the angle between these two velocities, V1 and V2, at two different points A and B, those are very closer points to each other. So this is delta theta. Okay, so I told this length is V1, this also V1 because we are considering at an instant but very small time interval delta t. So the change in speed is negligible. Both have the same speed V1, V1. So this is V1, this is V1 means this will be, these two will have the same angle alpha alpha because these in this triangle these two sides are the same length. So we know that in this triangle delta theta plus alpha equal 180. So that is delta theta plus 2 alpha equal 180. So I told that I am considering much small time interval delta t which is almost equal to 0. During that time the change in central angle is almost equal to 0. I want to find the direction of change in velocity at an instant because I want to find the acceleration at an instant. So if I want to find the acceleration at an instant means the points A and B should be the same, but we can't find at a point. Very closer points, if I consider delta theta will be almost equal to 0. Delta theta will be almost equal to 0. So if I put delta theta almost equal to 0, that means 2 alpha almost equal to 180. So alpha will be almost equal to 90 degree. That means the direction of change in velocity will be perpendicular to the velocity at an instant. The direction of change in velocity at an instant, because I need to find the acceleration at an instant. So to find the acceleration at an instant, I should know the rate of change of velocity, but it cannot be found at an instant because at a point there can't be two different velocities. So we consider much two closer points during a very shorter time. So when we find like that, the angle alpha becomes 90 degree means the direction of change in velocity at an instant means very close to small 2 points. Delta V is perpendicular to the velocity. That means direction of velocity, change in velocity is perpendicular to the velocity at an instant. Also we know that A is equal to acceleration equal to change in velocity over time. So delta V is perpendicular to the direction of velocity means at an instant, at any instant, the direction of change in velocity is perpendicular to the velocity at that instant means acceleration will be perpendicular to the direction of velocity at any instant when the object moves on a circular path. Okay, so this is the simple derivation to show the acceleration must be right angle to the velocity at an instant if the object moves on a circular path. So I can say the acceleration must be perpendicular to velocity at any instant. So acceleration perpendicular to the velocity means velocity along the tangent, so the acceleration must be towards the center. You can see the acceleration must be perpendicular this direction. So acceleration should be towards the center always, and it must be right angle to the direction of velocity. Okay, so this acceleration is called centripetal acceleration, center seeking acceleration, because that's the only condition we need to have a circular motion. The object should have an acceleration towards the center of the circular orbit. Okay, but can there be an acceleration along the tangent? Yes, there could be acceleration along the tangent. In that case, what will happen? If there are both acceleration, there is a component of acceleration towards the center of the circular path, and there is an acceleration along the tangent at an instant, means what will happen? The object will move on a circular path and the speed will continuously change. So the speed changes due to the acceleration parallel to the tangent, and it maintains a circular motion due to the acceleration which is perpendicular to the velocity. Again I am saying, if there are two acceleration or two components of acceleration, a component which is perpendicular to the velocity, that will keep the object in circular orbit, and the component of acceleration parallel to the direction of velocity along the tangent will change the magnitude of the velocity or change the speed of it. So, but anyway, mathematically there are some certain conditions we need to derive and get it, but in terms of acceleration we can say that in that situation the object will move on a circular path with varying speed. But if there is no acceleration along the tangent, but only there's an acceleration towards the center of the circular path, then the object will move on a circular path at constant speed. Okay. Okay, so next thing is about centripetal force. So just now we came across about centripetal acceleration. So there must be an acceleration towards the center at any instant during the circular motion. So if there is an acceleration towards the center at any instant, according to Newton's second law, F equal ma, is the centripetal acceleration, means there must be a resultant force towards the center, which is called centripetal force. So when object moves on a circular path, it should have a resultant force or a component of force always towards the center of the circular path. That is called centripetal force. So if the object has only one force such that always towards the center of the circular path, then the object will move on a circular path at constant speed. But when object moves on a circular path, if the object has always two different forces or two components of forces, imagine there's a force towards the center of the circular path and a component of force along the velocity, along the tangent, then what will happen? Due to the component of the force towards the center of the circular path, the object will move on a circular orbit, but due to the component of the force which is along the tangent of the circular path, the speed will continuously change. Okay, to have a change in speed, there must be a force or component of force along the tangent, and to maintain a circular motion, there must be a force towards the center which is perpendicular to the direction of velocity. This is centripetal force. This force increases or decreases the speed of the object in circular motion. Okay, so the next topic is centrifugal effect or centrifugal force. It's not much described in A-level syllabus, but it's better to know that, because without knowing it, sometimes we might get confused when you see some certain questions, or we might have confusion how circular motion happening when there's an unbalanced force towards the center, why the object is not moving towards the center. Sometimes students ask, so to have clear explanation about it, better to analyze about this centrifugal effect. Okay, so to explain centrifugal effect, first we should know about the property called inertia. So inertia is the property of matter to show or to resist the change in its position or change in its motion. Or we can simply say, what is inertia of a matter means it's the ability of it's a property of a matter to resist the state of change in its motion. State of change in its motion. Okay, simply I can explain the idea of inertia. Imagine there's a perfectly smooth horizontal surface, and if there's a mass of 1 kilogram kept on it, and if you want to accelerate it at 1 meter per second squared, we know the force required, that you need to apply a force to the object, is equal to F equal ma 1 into 1 Newton. So that means if I draw a free body force diagram for the object, there will be weight downwards, there will be normal reaction. We don't need those two forces, but you apply a force 1 Newton this direction, you will have a force in opposite direction according to Newton's third law. So that means who gave this force? The object gave it. How is it giving it? Because it shows its reluctance, or it's resisting the force you apply. It's opposing the force you apply, because when you apply a force only, it's going to change its state of motion. It was at rest. Now it's going to move after you apply. It's a perfectly smooth surface. So even if it is smooth surface, you experience a force in opposite direction. How did you get it? Or what's the origin of this force? The object gave it. Object gave it means object is showing its resistance to the force you applied on it. Okay, that is the idea of inertia. The same way, if you apply a force, if you want to accelerate a mass of 100 kilograms, so this is 1 kilogram, the force you need to apply is 1 Newton. Okay, if you want to apply, accelerate a mass of 100 kilograms at 1 meter per second square, then the force you need to apply if you use F equal ma will be 100 Newton, and you also will experience a force 100 Newton. That means it shows more resistance. That means if you want to accelerate at the same 1 meter per second square, when the mass increases, it shows more resistance to the force you apply. So that means higher the mass, more resistance means higher inertia. Okay, so that's the first idea you should know. That what is inertia? It's the, we can say simply, it's the property of a matter to resist the change in its state of motion. Or simply we can say it's the property of a matter to resist the acceleration provided to it. Simply we can say, because force, rather than saying state of change occurs if the object is at rest, and if it wants to move, it should accelerate. If the object is in motion and if it wants to slow down, it should decelerate. So always it opposes the state of its motion means we can simply say that it always opposes the acceleration provided to it. Okay, so we can say what's inertia? We can say it's the property of a matter to oppose the acceleration provided to it. Okay, so by using this idea, we can explain the centrifugal effect means, for example, okay, so consider a circular motion where a string is attached to a small sphere and it's kept on a smooth horizontal flow and it is moving on a circular path, uniform at a circular path. Okay, so if you think about the free body force diagram of the sphere, the weight is acting downwards and there is a normal reaction and there is a tension acting on it. The tension is provided by the string. Okay, so but if you think about the point where the string, the free end is connected at O. At O, what happens? The string, there will be a force towards the sphere. So how this force is exerted at O? The reason is the string is pulling the object or the sphere towards the center. When it pulls the object towards the center, it's not moving towards O. It has the tendency of moving away from the center, because you know the force, the R and mg balances each other. T is the unbalanced force provided by the string. So when T is there, the object will have acceleration towards the center, that is the centripetal acceleration, already I explained. So inertia means the property of the matter to oppose the state of change in motion means I can say that it's a property of the matter to oppose or resist the acceleration provided to it. So the acceleration is towards the center. If it wants to oppose that acceleration, it should have a tendency of moving away from the center. It should have a tendency, it's not moving away from the center, but it should have a tendency of moving away from the center. Since it has a tendency of moving away from the center, it's not falling or it's not moving towards O, it is able to provide a force, the same force at O. Simply we know that that's Newton's third law, because when the string pulls the sphere towards O, this will pull the point O towards it. We know third law pair of forces, but in terms of inertia, we can explain that the string pulls the or provide an acceleration to the sphere towards O. Due to inertia, it resists that acceleration, so it has tendency of moving away from the center. Since it has tendency of moving away from the center, it exerts a force on O towards it. That is the centrifugal effect. Okay, the centrifugal effect means it looks like, so if you are rotating by your hand, you might feel, so imagine you are holding it and you are rotating, it's on your hand, you will feel a force this direction. So you might feel the same force T, you will feel it on your hand. So you might think there is a force acting on the sphere away from your hand or away from the center. You feel there's a force acting on it, but actually there is no force acting, such force is acting. No, there are no such forces. It's actually the tendency of the sphere to moving away from the center causes or originate this force. So there is no such force away from the center. So this is called centrifugal force. So the tendency of the object to move away from the center is the centrifugal effect. By using this centrifugal effect, we can have a question. We had a question in the old past paper. Okay, so according to that question says on a smooth horizontal table, there's a tiny hole, a smooth edged tiny hole. The string is passing through the hole and two different identical masses, spheres of same masses are attached at the opposite ends of the string. By keeping the sphere P1 at rest, the sphere P2 is allowed to move on a circular path on the smooth horizontal table. So what happens here? So this sphere P1 is hanging below the hole, but this sphere is moving on a horizontal circular path. This sphere will not move or will not fall to the hole. But if you stop the circular motion, then it will come towards the hole. But when it moves on a circular orbit, the sphere P2 will not come towards the hole. The reason, when it moves on a circular orbit, there is a tension provided to the sphere by the string. That will be the centripetal acceleration towards the hole on the table. So due to inertia, what happens? The sphere P2 has tendency of moving away from the hole, or it shows resistance to the acceleration provided by the tension. So to show the resistance, it should have tendency of moving away from the hole. It's not moving away from the hole, but it should have the tendency of moving away from the hole. Because of it, it maintains the same radius and moves on a circular path. It will continue the circular motion forever if the surface is perfectly smooth. Okay, so this is a good idea to understand the centrifugal effect. So when we give this question, it's an old past paper question. First, most of the students ask, won't this P2 fall through the hole? No, it won't fall. Now you understand that it won't fall through the hole because of the centrifugal effect. Okay, so the idea of centrifugal effect, better to know to answer certain questions like this. Same way we can consider another good example for centrifugal effect. Imagine, take a small bucket and fill it with water. So fill it with water and rotate it on a vertical circular path. So rotate it on a vertical circular path like this. On a vertical plane, rotate it on a vertical circular path. Even when the bucket is upside down, if you maintain a particular speed, that we can get it through mathematical equations I'm going to derive. But anyways, simply we can analyze qualitatively. But when we consider this circular motion, even when the bucket becomes upside down, the water will not spill out of the bucket. If you think about the free body force diagram for the water, the two forces acting on the water which is kept in the bucket are the weight acting downwards, weight of the water acting downwards. Also the bucket is touching the base of the bucket, sorry, the water is touching the base of the bucket. So there will be normal reaction that also acting downwards, pushed by the base of the bucket on the water, also acting downwards. So both forces are acting downwards. There is no force in vertically upward direction. Still the water is not falling down if you maintain a particular speed. That we need to calculate in terms of equations. I am going to derive them. But even when the two forces are acting downwards, the water will not spill out. The reason, again, centrifugal effect. The water column is moving on a circular path. So I already derived, I already showed when I start this lesson. When object moves on a circular path, the acceleration should be towards the center. So when it is upside down, this is the center of the circular path. So the acceleration should be towards the center. So the acceleration should be towards the center means the water column or the water kept inside the bucket should have acceleration towards the center. Inertia means the property of the matter to resist the acceleration provided to it. So it should resist that acceleration means it should have tendency of moving away from the center. So it will try to move away from the center. If there's a tiny hole on the base of the bucket, what will happen? The water will come out like a fountain. It will come like this way through that because it has tendency of moving away from it. So that's the reason the water will come out of the hole like this. This idea is used in washing machines during the spin to remove water. The washing machine rotates, the clothes themselves will move away from the center because of their centrifugal effect. Until they touch the wall of the drum, they move away. So when they touch the wall of the drum, they still has tendency of moving away from the center. So they will press themselves with the wall of the drum. There are tiny holes on the drum. So when they press themselves with the wall of the drum, what happens? They will be pressed and water will come out and the water will be removed from the clothes. So that's the idea of centrifugal effect. Okay, so simply we can say in most of the situations, centrifugal effect maintains the circular motion. For example, simply we'll think like this. Small sphere is attached to a inextensible string of length L or length R or whatever it is. So this point is fixed on a smooth horizontal floor and the sphere which is kept such that the string is under tension without slagging. Okay, by giving a force or by applying a small push to the sphere right angle to the string, you started the circular motion, right? So what happens if you throw it in right angle to the string at a velocity v, and this is a smooth surface, smooth horizontal surface, what will happen? So due to the velocity what you provided, which is along the tangent to the circle, or you can say the velocity is provided such that perpendicular to the string, what will happen? The sphere will try to move on a straight line and it will try to reach somewhere here. But you know that if the sphere tried to reach a point little on the right side on the same straight line, the length of the string will be more than this length. But I told it's an inextensible string. So what will happen when you try to move slightly to the right, the length of the string cannot extend. So the string will exert a force, say a little bit on the right side. When I draw, the string will exert a force, tension on the sphere towards the center. So there will be a force, that is the tension towards the center, because if you try to move along this line, the length of the string should increase, but it's an inextensible string. So when the sphere slightly moves to the right, the string will pull or provide a tension to the sphere towards the end O. So you know that the tension which is provided is right angle to the velocity you provided, because it moved a little bit, that happened. So when the tension is provided towards the center, there will be an acceleration towards the center. So when there is an acceleration towards the center, due to the inertia of the sphere, it will have a tendency of moving away from the center. So it will have tendency of moving away from the center, but it won't move away from the center. So it try to move away from the center and keep the tension always there. So what will happen? Always it will move on a circular path. Always it will move on a circular path such that the string never sag or never the sphere moves towards the center. It will maintain the circular motion at constant speed, because this is the only force acting on it, the tension. There is no other force acting on it. So it will maintain the circular motion at constant speed. Okay, so it has tendency of moving away from the center, because of inertia, but it won't move away from the center. Due to that tendency, the tension will remain on the slag or on the string, and the string will not sag. So it will continue to move on a circular path. So the centrifugal effect of the sphere maintains the circular motion. Okay, so now I'm going to derive an equation for centripetal acceleration at an instant. So I'm going to derive an equation for centripetal acceleration at an instant, means at a point. Say I want to derive the equation for the centripetal acceleration at point x. Okay, so x and y are, as I explained in the beginning of this start of this lesson, x and y are two very closer points on the circular path. So here I am not saying the particular object is moving at constant speed, or I am not saying assume the particle is moving at constant speed. No, I am not saying anything. It might move at different speed at different points. It could have different speeds because it might have acceleration along the tangent also. But I showed the two speeds at x and y as same vv. The reason, x and y are very closer points. That means the time taken to move from x to y, that is delta t, the delta t is almost equal to 0, but not equal to 0, very smaller time. So very smaller time means x and y are much closer points, almost overlapping points. So there is no significant change in the speed, but it might have different speed at different points. But x and y are, again I am telling it, they are very closer points, almost the same points, but I showed it like an enlarged diagram. Okay, same thing as I told earlier. So there's a change in velocity. So delta v is equal to final minus initial. I'm considering a smaller time interval delta t, which is almost equal to 0. So I can say vf is equal to vi plus delta v. If I draw a vector diagram for this, the final initial velocity, this direction, that is equal to v, the speed. The final velocity is vf along this way. I drew it like that. That also I showed same magnitude because much closer points x and y are. The object might move at different speed, doesn't matter, but I am considering two much closer points, very closer points, almost the same points. So during that smaller time, the change in speed is negligible. So I take it that also v, the final speed, as v. So the change in velocity is delta v, this one. So as I explained in the beginning of this lesson, this angle, if I draw this angle will be equal to delta theta. This angle is equal to delta theta. So this is also delta theta. This one also delta theta. Okay, I showed already these two angles are 90 in start of this lesson. Okay, so in this triangle, I can say this is much smaller angle. So in a smaller angle, whether it's a straight line or curve, I can say delta v is equal to v delta theta. Divide this by time, delta v over delta t is equal to v delta theta over delta t. So delta v or delta t is the acceleration. A equal v delta theta over delta t. Keep it as first equation. Okay, when I consider this small segment from x to y, that delta s, so there I can say delta s is equal to r delta theta. Divide this by the time delta t, so delta s over delta t equal r delta theta over delta t. Delta s over delta t is speed. Here I won't say it's an average speed because I consider this delta theta is a very small angle. X and y are much closer points. So delta s over delta t is the instantaneous speed at point x. Instantaneous speed at point x, which is v equal to r delta theta over delta t. This is equation 2. Okay, so I almost finished the derivation. So in this one, A equal V delta theta or delta t. So from this I can uh, write delta theta or delta t as a subject. So I'll take that as a second equation. So from this I can say delta theta over delta t equal V over R. Keep it as second equation. So substitute second equation in first equation. I'll get A equal V times so delta theta or delta t V over R. So that means V squared over R. This is the centripetal acceleration. I already derived that the centripetal acceleration is perpendicular to the velocity at an instant. So this is the centripetal acceleration at an instant at point x. Okay, so this could be derived more precisely by using polar coordinates and vectors. I'll do it at the end of this lesson. I'll show that it's a slightly different method, but normally in physics they won't ask because there we need to use calculus a lot. So, and also there we can get the acceleration along the tangent also. I'll derive that one. But in A-level syllabus, they follow this method of derivation, or you can derive by using two triangles, considering by using similar triangles. That also you can use. Sometimes certain books they derive like that. But remember that the students have confusion because when we put here and here V, students thinks this derivation is valid only for motion in circular path at constant speed. No, this is valid even when the speed changes during circular motion. We can use this equation for an acceleration at an instant, because in this equation I did not say it's moving at constant speed. I say the speed could change, but x and y are since much closer points. Why I take much closer points? Because I want to find the acceleration at an instant at point x. That's the reason I took both speeds v, because at the same point the speed is the same even when there's a small change in time. Okay, so the time taken to complete one full circular path is called time period, denoted by capital T, and the number of orbits completed per second is called frequency. You know the relationship between frequency and period, T equal 1 over f. So that will be the second equation. Next thing is about angular speed. So angular speed, so that means when an object moves on a circular orbit, imagine the object is initially at this position at t equals 0. It's moving in this direction, and later at time t equal t, the object has come to this position. The change in central angle is theta. Okay, so what is angular speed means? Rate of change of central angle is defined as angular speed. So angular speed is denoted by omega, that is rate of change of central angle. Means calculus we put d theta over dt, d theta over dt, and it's denoted in mathematically theta dot. But we are not going to use these in physics. So we say change in central angle. Initially the angle is theta 0 at t equals 0, theta equals 0. At time t equal t, it's theta. So we write omega equal theta over t, and we define theta as change in central angle. So theta is a change in central angle. Unit of omega, theta should be in radians, and this should be in second. So the unit of omega, radian per second. So the second, third equation, omega equal theta over t. Okay, all syllabuses use this one. Edexcel, Cambridge, International Baccalaureate, they all use this equation. Okay, what could be the third equation? We say when it completes one full circular path, the change in central angle will be 2 pi radians, and the time taken will be 1 period t. So it's a standard equation, omega equal 2 pi over t. Same way, we know that t equal 1 over f. So if you substitute t equal 1 over f, omega equal 2 pi f. That also taken as standard equation. Okay, so the next equation, we consider a motion. So when it moves from this point to this point, let the distance move is s. It could move at different speeds, so I can consider here also a much closer point, delta s. Imagine these two are much closer points. Again, we consider this as delta t and this distance is delta s. Okay, so the radius is r. So we know that we are going to get the next equation for the speed. So this will make it as delta theta. So we can say delta s is equal to, in this triangle, this segment delta s is equal to r into delta theta. Divide both sides by using time. Delta s over delta t equal r delta theta over delta t. Here we assume these 2 points are much closer because I want to get at an instant again, right? So these 2 points are much closer points. This is at t equals 0. This is at time delta t. Little later, delta t also almost equal to 0. So delta iso delta t is the speed at an instant. I can say that's a speed at this point. When t becomes very small, I can say that's the speed at this point because time is much smaller. So that is v equal r. Delta theta or delta t, rate of change of central angle is omega. V equal r omega. Next equation. So this also we can use at an instant. This we use at an instant. This we use at an instant. So at a particular instant, the speed might be v, omega might be a particular value, but later it might change. The speed might increase, so omega also will increase later at another time. Okay, so we can use this at an instant, right? So then we can write equation A equal v squared over r. Instead of v squared, we can put r omega. I'll write it here. A equal v squared over r. Instead of v squared, we can put r omega, all things squared over r. Solve it. R squared omega squared over r omega squared. That also taken as standard equation. So finally, the equation centripetal force F equal ma, that is F equal mr omega squared. Here also we can write an equation for centripetal force. I forgot to write it. F equal mv squared over r. That also a centripetal equation. Here A equal v squared over r. F equal mv squared over r. Centripetal equation. Centripetal force. So these are the equations you must know to answer the questions in physics, unit 4 and Cambridge also. Okay, next thing is conical pendulum. Conical pendulum means a bob attached a string and a light inextensible string, and the bob moves on a horizontal circle and the string makes an angle theta with vertical. So application of this is merry-go-round. Okay, when you think about the free body force diagram for the bob, there will be weight downwards and there will be tension along the string T. That makes an angle theta with vertical. This is theta, means this is also theta with vertical. So since the bob moves on a horizontal circle, there won't be any resultant force in vertical direction according to Newton's first law. So in vertical direction we can say T cos theta minus mg equal to 0. So T cos theta equal mg. I can take it as first equation. O is the center of the circular path. We know centripetal force must be towards the center of the circular path. That's the resultant force towards the center of the circular path. So here the resultant force towards the center of the circular path is provided by the horizontal component of the tension. So that will be T sine theta is the centripetal force. F equal T sine theta. It's a centripetal force that must be equal to mv squared over r. So here v is the speed at which it's moving in horizontal circle. So there is no component of force. You can imagine the free body force, and there is no component of force parallel to the direction of tangent. of the circular path, or there is no component of force parallel to the direction of velocity. Therefore, it will move at constant speed here, right? So t sine theta equal mv squared over r. R is the radius of the circular orbit. So this is the radius of the circle. This is the radius. Here I can mark it here. This is the radius from O to the center of the bob is the radius. So we can consider this as the second equation. Divide second equation by first equation. That's the way we normally solve in questions also related to merry-go-round or conical pendulum. So t sine theta over t cos theta equal mv squared over r over mg. T and T will get cancelled, sine over cos equal tan theta. So finally here the m will get cancelled. So we will get finally tan theta equal v squared over rg. So it's not a standard equation. Normally several times the past papers they ask to derive this equation. You should be able to derive by using this method. Okay, so when an aeroplane turns, it bends like this. You would have noticed that. So there, the weight of the aeroplane acts vertically downwards. There will be a lift due to the buoyancy effect. So there will be lift which is perpendicular to the wing of the aeroplane. So this is the lift. I can mark it L. That is perpendicular to the wing. So this is 90 degree. So if this is theta, this also will be equal to theta. So this will be 90 minus theta. So this angle will be equal to theta. You can see this is theta, means alternative angle. This is theta. But this angle is 90. So this will be 90 minus theta. But this is 90. So 90 minus theta equal to theta. So this angle is theta. That means the angle between the lift and the weight is equal to theta. So here if it is moving, it moves at constant speed. So here since it's moving on a horizontal circular path, the resultant vertical force must be equal to 0. So that means we can say L cos theta minus mg equal to 0. So L cos theta equal to mg. So the required centripetal force is provided by the horizontal component of the lift towards the center of the circular orbit. O is the center of the circular path. So towards the center of the circular path, L sine theta, if you use Newton's second law, if equal ma, L sine theta equal to m. A is the centripetal acceleration, which is v squared over r. So we assume at an instant the speed is v. Okay, so divide this as a second equation. At an instant speed is v. Okay, divide the equation 2 by 1. L sine theta over L cos theta equal mv squared over r over mg. So L will get cancelled. Sine over cos tan theta equal v squared over rg. Exactly the same thing like what we derived for conical pendulum. Here also you will get it. Okay, vertical circular motion at variable speed. So the speed and the angular speed both changes. For example, when you attach a small sphere like a bob to an inextensible string of length L, and the other free end is attached to a small horizontal nail, smooth nail, and initially hold the sphere in horizontal position, such that the string is in horizontal position under tension, then release it. So it will move down from rest. Initially the speed is 0. So string will move on a vertical circular, the bob will move on a vertical circular path. Okay, so when the bob comes to this position, so when the bob comes to this is at t equal 0, this is later at time t equal t, variable time t, so variable time t equal t. The bob has come to this position, so I'll draw it with solid line. That makes an angle theta with vertical line. The length of the string is L. That's going to be the radius of the circular orbit. How to find the speed? So if we ignore or neglect the drag force, or if the drag force is not significant, when the bob moves from this position to this position, it has fallen through a vertical height h. So there will be loss in gravitational potential energy. So due to loss in GPE, there will be gain in kinetic energy. So I can say loss in GPE equal gain in K. So at this instant, the velocity will be along the tangent. At this instant, there will be velocity along the tangent. I'll explain about the forces at this instant. First, we'll find how I'll show how to find the speed. So there I can say loss in GPE equal gain in kinetic energy. Loss in GP equal mgh. So h is in this triangle, in this right angle triangle. This is theta, means this is theta. So h equal to L cos theta. You can say in this right angle triangle, h equal L cos theta. So I can say loss in GPE mg h equal half mv squared minus half mu squared, gain in kinetic energy. Okay, so here this is L, this angle theta, it makes an angle theta with vertical line. So this is alternative angle, so this is also theta. So the height h in this triangle, this will be L cos theta. So mg L cos theta is equal to half mv squared minus, I said initially it was kept at rest and released from rest, so 0. Okay, so m and m will get cancelled, so I can say v squared equal to 2gl cos theta, and v is equal to square root of 2gl cos theta. So here you can see when the theta varies, when the sphere changes its position on the circumference of the circular path, the theta will change. When the theta changes, the speed also will change. Okay, so when it moves from here to here, we know that it's losing the GP. So it's going to gain kinetic energy, means the speed is going to increase. Why this happens? What's the reason for that? We'll think about the forces acting on the sphere. So when the sphere is at this position, position X, at the position X, if I draw the free body force diagram, it has weight downwards mg, and there's a tension towards the center O that makes an angle theta with the vertical. Okay, so we know that centripetal force means the resultant force towards the center of the circular path. Already we discussed it earlier. So centripetal force is due to the resultant force towards the center of the circular path. So that is going to be along this direction towards the center of the circular path. Resultant force is T minus mg cos theta at an instant. So here also you can see the centripetal force is changing, varying, because theta changes. Centripetal force is going to change. T minus mg cos theta equal to mv squared over r. R is L, length of the string. So here V also changing. So we can find the tension at an instant when theta makes angle, when the theta, when the string makes an angle theta with the vertical. So T is going to be mv squared over L plus mg cos theta. So by using it, we can find the tension at an instant. Okay, so here I'm using the equation mv squared over r. mv squared over r, I'm using it. So that means the speed is changing. Different points, the speed will be different. At an instant, I found the tension. Okay, so what's the reason the speed is changing? Now you can see, we can think about the component of the force along the tangent. Along the tangent means which is perpendicular to the radius or perpendicular to the string. Can there be a component of force? Yes, there will be. If I think about a force which is perpendicular to the string, this direction, what could be the force along the tangent? I'll say Ft, tangential force Ft. What could it be? So this string is perpendicular to this tangent. So this tension has no component. But Ft will have component due to the weight. If I say this theta, this is 90 degree, so this is going to be 90 minus theta. So this force, this angle will be 90 minus theta. So due to the component, there will be force along the tangent, that is going to be Ft. The force which is along the tangent, I put it T, that is going to be mg cos 90 minus theta. So you know that cos 90 minus theta, sin theta, in mathematics you would have learned it. So that's going to be mg sin theta. So if I use Newton's second law along the tangent, F equal ma, so mg sin theta equal ma a t. T stands for acceleration along the tangent. So that's going to be at, the acceleration along the tangent is going to be g sin theta. So due to this acceleration, which is not centripetal acceleration, it's acceleration along the tangent. Due to that acceleration, the speed is changing. Okay, we discussed earlier that about centrifugal effect. Good example, when you rotate a bucket in vertical circular motion at a particular speed, okay, at the highest position, to maintain a particular speed, by maintaining a particular speed at the highest position, we can keep the water inside the bucket without its falling out or without spilling out. So how to find the minimum required force? Okay, we'll think about the free body force diagram for the water inside the bucket. So I think about the free body force diagram for the water inside the bucket. So the water has weight downwards, it's acting vertically downwards, mg. And I told when it moves on a circular path, it has the intention of moving away from the center. So the water will push the base of the bucket because it has intention of moving away from the tendency of moving away from the center. So when it pushes the base of the bucket, there will be pushed by the base on water downwards. That is the normal reaction. I can mark it R. That is R. Okay, so the total force acting on the water inside the bucket is R plus mg, which is downwards towards the center of the circular path. So that will be the centripetal force. So the centripetal force should be towards the center of the circular path. That is F equal mg plus R. That must be equal to mv squared over R. Okay, so we'll make R subject. R is equal to mv squared over R minus mg. Okay, so the condition mathematically to say that water is still inside the bucket and not falling out means the water should have contact with the base of the bucket. That means still the water is at the inside the bucket at the highest point. That means R should have a real positive value. So if I say mathematically R has a real positive value, that means the water is still inside the bucket even at the highest point. So they are the condition to have to keep the water inside the bucket. R must be equal or greater than, we normally say R greater than 0, or equal also we can put, but R generally mathematically we say should be greater than or equal to 0. So R greater than or equal to 0 means this quantity also must be greater than or equal to 0. Now we'll think about this one, that is mv squared over R minus mg should be greater than or equal to 0. Bring it to the right, mv squared over R greater than or equal to mg. So m and m get cancelled, cross multiply, v squared must be greater than or equal to gr. So v must be greater than or equal to square root of gr. So you learn that in O level, that means x greater than 5, x greater than 5 means, or greater than or equal to 5 means the minimum value of x is 5. So here minimum value of speed to maintain circular motion such that water not spill out of the bucket is equal to square root of gr. R is the radius of the circular orbit in which the bucket is rotated, and G is the gravitational acceleration on Earth, 9.81 meter per second square. Okay, when object is allowed to move on a vertical circular path freely, such that earlier explained, a small sphere or bob attached to a string and allowed to move on vertical plane, the speed will continuously change due to change in gravitational potential energy. You can't keep the speed constant here. Okay, so you can't keep the speed. If you're allowed to move freely, you can't keep the speed as constant, because you know the gravitational potential energy is changing when it moves down, so kinetic energy will continuously change and speed will change. Or motion of a small marble inside a vertical track. If you throw a small marble or sphere inside a vertical loop or vertical track, when it moves here, the speed will continuously change, so it won't keep the speed constant there. So if you want to keep the speed constant, there should be external work on it. For example, something like you can keep a small toy car inside a track. Imagine inside a vertical track, you can have a small toy car which is driven by a battery or power supply. Then you can keep the circular motion inside at constant speed. Okay, we'll analyze that situation. So there we normally consider three different positions. Lowest position, the position at horizontally, here Y, and the highest position Z, X, Y, Z. Okay, so at X, we'll think about the free body force diagrams at different positions. So for that, normally we take, when we are deriving this, we normally arbitrarily take a position something like here. This is the O, at a position where it makes an angle theta with vertical. Okay, we can say it's moving at a constant speed V. So the speed is constant V at this position. Okay, so then we'll get a general equation in terms of theta. Then we find the specific values for the normal reactions at X, Y, and Z by substituting the proper values for theta at these positions X, Y, and Z. Okay, at position this one, arbitrary I took a position, so I can name it P. At P, what happens? If I draw the free body force diagram for at P, so I'll draw the car as a small sphere, easy to draw. So there will be a normal reaction, this direction R from the track. The weight will act vertically down mg, and this angle theta means this also theta. Is also theta. It's moving at constant speed. We know the resultant force towards the center of the circular part is called the centripetal force. So this angle also theta, opposite angle. So the centripetal force towards the center at P is going to be, at P, centripetal force towards the center, which is O, is R minus mg cos theta is equal to mv squared over r. R is the radius of the circular path. So R is going to be mv squared over r plus mg cos theta. Okay, so R, this is the general equation. So I can say at X, theta equal to 0. So cos 0 equal 1. So R will be mv squared over r. Cos 0 1. So plus mg. Then at Y, theta equal to 90 degree. Cos 90 0. So R will be equal to mv squared over r cos 90 0 plus 0. So I don't need to write it. Same way at Z, theta will be 180. cos 180 is minus 1. So r is going to be mv squared over r cos 180 minus 1 minus mg. But at the same time, the v, I told that it's maintaining a constant speed, but constant speed cannot be a random value because if it is continuing the circular path at constant speed, it has to be, the v has to be a specific value as I explained earlier, because r must be a real positive value. So r must be greater than 0 or equal to 0. So if there is no clip or anything with the vertical track, the wheel has no clip if it is allowed to move freely at constant speed by using a battery or whatever it is, then it has to satisfy the condition, this one, otherwise it will fall down at the highest point. So here we know that the minimum speed they have to maintain throughout the motion should be greater than or equal to square root of gr. Okay, so this type of questions also can come. Okay, so that's the end of theory in physics related to circular motion. In my next video, that is the during my second lesson of circular motion, I'll discuss exam style questions related to circular motion. So before doing that, that will be in the second lesson. So as I told earlier, now I'm going to derive the equation for centripetal acceleration by using polar coordinates. Okay, so but for physics you don't need this derivation. They won't ask this derivation in physics exams, but just for understanding I'm doing it. Those who have difficulties understanding calculus, you can just ignore this derivation. In my second lesson I'll discuss questions, exam style questions related to circular motion in physics. This is useful for students those who are doing further mechanics or further mathematics. Okay, so here the polar coordinates theta and I and j are the unit vectors along x and y directions. Okay, so the vector r is given by r cos theta I plus r sin theta j. I and j are the unit vectors along x and y directions. Okay, so the velocity, the vector velocity, vector v is given by dr over the derivative of r related to time. That's the velocity, dr over dt. So here, if I differentiate this with respect to time, you will get r. Cos theta, when you differentiate, you will get sin theta, that is minus sin theta, into theta dot. Theta dot means d theta over dt, that is the angular speed. Theta dot means d theta over dt, that is the angular speed, rate of change of central angle, into I plus r sin theta. If you differentiate, cos theta into theta dot in j direction. Okay, so that is the speed vector in terms of the unit vectors I and j. Okay, so you know that if there is a vector r equal xi plus yj, the numerical value or the magnitude or modulus of this vector is given by square root of x squared plus y squared. Okay, so what could be the speed? I'm going to find it. Okay, so we'll find the speed that is equal to square root of r squared minus square will become square, r squared sine squared theta, theta dot squared plus r squared theta dot squared cos squared theta, square root of it. Okay, so that's going to be v is equal to, we can take r theta dot squared out of the square root. So it will become r squared theta dot squared, r squared theta dot squared. We will take it out of the square root. It will become r theta dot. So it will become r theta dot within square root sine squared theta plus cos squared theta We know that sine square theta plus cos square theta equal to 1. So that's going to be r theta dot. So theta dot is angular speed omega. So that is v equal r omega. So that's the speed at an instant at time t equal t at an instant. Okay, now we'll see what could be the direction of this speed. Okay, so we find the speed, but what could be the direction of velocity? Will it be along the tangent or will it be towards the radius or some other angle? We will find it. So what could be the velocity direction? So at that instant the speed is given by minus r sine theta theta dot I. So that means I will mark it by using the x component here. That is minus sign here, minus I is taken towards right, so minus I, this minus I can put it with the I, minus I, that means towards left. So towards left the component will be r sine theta theta dot, r sine theta into theta dot, or r theta dot sine theta, r theta dot sine theta towards left, and this is r cos theta theta dot along the j, so that could be along this direction, r theta dot cos theta. I'll remove this t equal t. Okay, so we'll find the velocities. These are the components of velocities at time t. We'll find the resultant velocity. Now this is the speed I found it, right? R omega. We know that. We already used that in physics also. V equal R omega. I got it. But I want to find the direction of the velocity. So towards left, opposite to the direction of I. Why should I take it opposite to the direction of I? Because I'm taking here minus sign. So minus sign, I can put it with minus I. So minus I means opposite. I is taken towards right. So minus I is towards left. That will be r theta dot sine theta. Towards up, along the direction of unit vector j, r cos theta theta dot r theta dot cos theta. Okay, so we'll find these two components are the velocity at time t. We will find it along the tangent and along the radius or towards the O. What could be the resultant velocity along those directions? Okay, to find the directions along O, along the tangent, we'll resolve them along the tangent. This is the along the tangent, we'll resolve it. Okay, so this is theta. If this is theta, this angle we can extend it this way. So this is theta means this is theta. This is going to be 90 minus theta. So this angle, this is theta, this is also theta, alternative angle. So this will be 90 minus theta. So this will be theta. Okay, we'll find it along the tangent, the green color, because that is perpendicular. This is 90 degree. This is 90 degree. So this is theta, this is theta, this green color and black color 90 degree because this is tangent. So this is theta means this angle with the tangent, this horizontal component minus j direction makes an angle 90 minus theta. The minus I makes an angle 90 minus theta. The j makes an angle theta. Okay, so we'll find along the tangent what could be the resultant velocity along that direction. Along the tangent, we'll find it. So that will be this component into cos 90 minus theta. This component means I wrote this one with the minus sign. I used it to resolve towards left. So that's going to be r theta dot sine theta along this direction. Velocity along the tangent. I'll put vt. Velocity along the tangent. How much will it be? r theta dot sine theta, r theta dot sine theta into cos 90 minus theta. Cos 90 minus theta is sine theta into cos 90 minus theta sine theta. Then if I resolve this one along the tangent, r theta dot cos theta into cos theta. So that's going to be r theta dot sine square theta, sine theta into sine theta, sine square theta plus r theta dot cos square theta. So r theta dot, if I take it common, r theta dot sine square theta plus cos square theta, that is 1. So r theta dot, that is r omega. That is the velocities along the tangent. Velocities along the tangent, we know that. So which is r omega. We already learned that in physics. So here we are getting in terms of polar coordinates also, we are getting along the tangent, which is equal r omega. Okay, what could be the velocity towards O? We will find it. So we'll resolve these two components along the radius. So that is towards O, we will resolve it. So this is, we have done it already. So I'll erase it because we have done it already. So we'll resolve all the velocities, the components towards O. So towards O, we will center seeking velocity. How much will it be? Towards O, we will find it. I'll put VO towards O. I should resolve r theta dot sine theta, sine 90 minus theta. So that is r theta dot sine theta times, this should be resolved perpendicular to the tangent, that means along the radius, means sine 90 minus theta. Sine 90 minus theta is cos theta. So r sine theta into cos theta. When I resolve this along the radius, it's going to be this direction because it has to move away from the tangent. So that is going to be away, opposite direction. So minus r theta dot cos theta into sine theta. This angle theta, move it away, sine theta. So that's going to be r theta dot sine theta cos theta minus r theta dot sine theta cos theta. So that's going to be 0. So that means there is no velocity towards the center. We know that when an object moves on a circular motion, there can't be any velocity towards the center of the circular orbit. That also we got it from this derivation. We are not saying like what we derive in physics, we take two closer points and we say the time taken is delta t and those. And here we are not using anything. At an instant I am using polar coordinates. Okay, this is more accurate and easy to understand the principles here. Okay, so the next thing is I should think about the acceleration. So we know the velocity vector, we got it. The velocity vector is minus r sine theta, theta dot I plus r cos theta, theta dot j is the velocity vector. To get the acceleration, I should differentiate it again with respect to time, is it? So this we got the conclusions. Okay, now we are going to get the acceleration vector. So acceleration is equal to dv over dt. Differentiation of velocity with respect to time is the acceleration. So velocity we know that minus, that is d over dt of minus r theta dot sine theta, r theta dot sine theta I plus r theta dot cos theta j, that is acceleration. Okay, we'll differentiate here. Theta could vary with theta is varying with time. Theta dots is the angular speed, that also could vary with time, is it? In vertical circular motion we learned that when a string attached to a point which is carrying a small sphere when it allowed to move, the speed changes. When the speed changes, according to V equal r omega, omega will change. So there will be derivative for omega also. Omega is depending on time, it's not a constant. So we'll differentiate that also. So when we differentiate d theta dot over d theta, sorry, dt is denoted as theta double dot, that is angular acceleration. That is called, this is theta dot is the angular speed. D theta dot over dt is denoted by theta double dot, or that could be denoted d2 theta over dt2, that is the angular acceleration. Okay, we'll differentiate it. It'll lot of things will come, we'll see. So when I differentiate this with respect to time, okay, so we'll differentiate the UV format. R is a common factor, so we'll take it minus R. I'll keep this constant theta dot. When I differentiate sine theta, it will become cos theta into theta dot I, is it? Minus R theta dot, I wrote it. differentiating sine theta, you know that when I differentiate sine theta with respect to time, sine theta, you know that I am skipping little d over dt of sine theta. I can say d over d theta of sine theta into d theta over dt. I didn't write that too much of steps. So this will be cos theta and into theta dot. So that's what I wrote, r theta dot. This r theta dot is this one, minus r theta dot sine theta, which become cos theta into theta dot. Okay, so I didn't show this way because then the steps will become a lot. So to avoid it, I just skipped a little bit. Okay, plus I will differentiate this one. So sine theta, I will write it. So sine theta, so the minus sign, I'll keep it here. So I put it as minus here. This minus sign, I'll put it here. Sine theta into differentiating theta dot with respect to time, it will become theta double dot. So r sine theta, so r is there, sine theta, r sine theta into theta double dot I. Okay, so that's the differentiation of this first part. Sine theta, r sine theta, d theta dot over dt is theta double dot I. This minus sign from this one. Okay, we will differentiate this one now. Plus r theta dot. If I differentiate cos theta, it will become minus sine theta with respect to time. So minus sine theta, differentiate theta with respect to time, theta double dot j, is it r theta dot cos theta, if we differentiate sine theta, theta double dot, plus r cos theta, different r cos theta into differentiate theta dot, theta double dot j. Okay, a lot of things are there. That's a small mistake. R theta dot cos theta become minus sine theta into theta dot, not theta double dot, theta dot. Okay. Okay, so this I can write like this way, minus r theta dot cos theta theta. So that means r theta dot squared minus I, here also r sine theta, theta double dot minus I. So I'll take minus I outside. So I'll say it like this, r theta dot squared, r theta dot squared cos theta plus r theta double dot sine theta minus I. I can write this way, no? Because I took minus common, I put it with the I. R theta dot theta dot theta dot squared, r theta dot squared cos theta plus r theta double dot sine theta minus I, plus here also r theta dot theta dot squared minus j. This I can write this way. So I can write this one as like r theta dot squared sine theta. Sorry, I can write this one first. R theta double dot cos theta minus r theta double dot cos theta minus r theta dot squared sine theta j. I put the j in positive direction. So only thing, this minus sign is here. R theta dot squared sine theta j. This one is positive. So r theta double dot cos theta. That is positive direction. Okay, so this is in minus I direction. So the same diagram, if I use it here again, I don't want this. So this is minus I direction. So I can say all these whole thing, this whole thing as AI, which is minus direction. So this is AI in I direction to the left because minus I. This is J direction, which is positive. So A j, acceleration in j direction. This is acceleration is minus side, so to the left. Okay, so this is ai, I took it, right? This is a j, I can call this whole thing as a j. Anyway, okay, so now I want to resolve ai and aj along the radius that is perpendicular to the tangent, and along the tangent we'll resolve it to find the component of acceleration towards the center and along the direction of velocity. We'll find the component of acceleration. So here ai cos 90 minus theta. If I want to resolve this along the we'll resolve it first towards the center. So towards the center, so this is going to be ai sine 90 minus theta. You can see that if I resolve the ai, which is towards left because minus I, ai sine 90 minus theta, that's going to be cos theta. ai sine 90 minus theta, which is cos theta. When I resolve aj, aj is going to be this direction minus aj sine theta. So the acceleration towards the center, that's a centripetal acceleration. Centripetal, I put it AC. C stand for centripetal towards the center. That's going to be AJ. I call this whole thing as AI. So that is AI, that is AI sine 90 minus theta, that is cos theta minus AI cos theta, because this is AI. I call this as AI to the left because minus sign. So AI cos theta minus, because when you resolve this AJ along the radius or along this line, it's going to be opposite direction away. So AJ, this is AJ, the whole thing is AJ sine theta. Okay, so we'll multiply all these things with cos theta. So r theta dot squared cos theta and cos theta cos square theta plus r theta double dot sine theta cos theta, r theta double dot sine theta cos theta. I am considering along the towards the center, that is the centripetal. R theta dot square cos square theta plus r theta double dot sine theta cos theta plus this one when I consider r theta double dot. This is whole thing is taken as aj into sine theta. So r theta double dot sine theta cos theta minus r theta dot squared sine square theta. So that is sorry, this is minus side. So one minute, I think I mean minus here. There's a small mistake. So that is minus here, minus. So that is minus into minus. I made a mistake here. So this is for this component, right? This is minus here. So minus r theta double dot cos theta sine theta cos theta minus plus r theta dot squared sine theta into sine theta sine square theta. Okay. So here you can see that r theta dot squared cos square theta plus r theta dot squared sine square theta. So I can say r theta dot squared cos square theta plus sine square theta plus r theta double dot sine theta cos theta minus r theta double dot sine theta, but they will get cancelled. So that will be 0. So that's going to be sine square theta plus cos square theta is equal to 1. So r theta dot squared. So acceleration towards the center, that is centripetal acceleration, r theta dot squared. Theta dot is angular speed omega. So it's going to be r omega squared. AC equal r omega squared. But we already derived it. V equal r omega. I derived it earlier. So I raised it at the start of this this derivation. I showed that V equal r omega is the speed velocity along the tangent. So instead of omega, I can put V equal r omega. Instead of omega squared, I can put V squared over r if I substitute. the centripetal acceleration equal r into v squared over r squared, that is v squared over r. See, we are getting the same answer as what we derived in method what we normally use in physics, where we take two close-up points. But here, by using polar coordinates, we are getting the centripetal acceleration v squared over r. Here I never used whether the speed is changing or not, nothing. Just I am taking at a point what could be the acceleration at an instant. And centripetal acceleration v squared over r. Okay, so we'll next check whether that, so this is the centripetal acceleration towards the center. Next we'll check, can there be an acceleration along the tangent. I told that if there is a component of force along the tangent, there will be acceleration along the tangent also. For example, application when you let a sphere attached to a string and let it move in vertical plane, yes, there will be acceleration along the tangent. We will find out what could be that acceleration. Okay, so for that, so I'll got the equation for this one, so I am now placing it. So what could be the acceleration along the tangent? So I'll put it as AT along the tangent, this direction along the tangent. What could be the acceleration? AT, I'll put it along the tangent. What could be the acceleration? So for that I should resolve AI cos 90 minus theta plus AJ cos theta. AI means all these components, the whole thing is I named AI cos 90 minus theta, so that is sin theta, plus AJ cos theta. We'll find out what could it be. So that is going to be AI cos 90 minus theta, so I'll write it as sin theta along the tangent. AT I put it, AT stands for acceleration along the tangent. AI sin theta plus AJ cos theta. AI sin theta, so this must be multiplied by sin theta. This is the AI, I earlier denoted this as AI. So that is r theta dot squared cos theta sin theta, or sin theta cos theta, plus r theta double dot sin theta into sin theta sin squared theta, plus this is the AJ into cos theta, so r theta double dot cos theta into cos theta cos squared theta minus r theta dot squared sin theta into cos theta. So this is the acceleration along the tangent. So here you can say r theta dot squared sin theta cos theta, r theta dot squared sin theta cos theta, here minus sign, here plus. So these two are going to get cancelled. So these two factors, that r theta dot squared sin theta cos theta plus here r theta dot squared sin theta cos theta minus will get cancelled. So which is going to remain? It's going to be r theta double dot sin squared theta plus r theta double dot cos square theta. So it's going to be r theta double dot sin square theta plus cos square theta. That's going to be 1. So r theta double dot. So the acceleration along the tangent is equal to r into angular acceleration. Theta double dot means d2 theta double dot means, so you know that theta double dot means d omega over dt or d2 t over dt2. That is the angular acceleration. So the acceleration along the tangent is going to be the radius r into angular acceleration. So if the angular speed is changing, there will be angular acceleration along the tangent. So that happens when a string attached to a small sphere moves in vertical plane, there will be angular acceleration. Okay, so I have done all the theories related to physics, and now I did mathematics. I told this is not in physics syllabus, but those who are doing mechanics, it will be useful to find out, and it's more clear to understand the derivation, because students normally get confused when I say when the books or whatever they say about when they are using the derivation in physics, they take two different points and they say assume the speed is constant, or the speed is the derivation when they do, they say normally it's a uniform circular motion. So then students ask, can we use the equation a equal b squared over r for a circular motion in which the speed is changing? Yeah, so to get out of those confusions, this is very good method of derivation in mathematics. But even what I did in physics, I told that we are taking too much closer points where the change in speed is negligible, but actual speed in the circular path could change. Okay, so we are using the equation a equal b squared over r at an instant. Okay, so at any instant we can use that when it moves on a circular motion. I hope you understood all these derivations. So in my second lesson, I'll do questions related to exam type questions. Okay, I hope you understood all these things. Bye.